With Unit 10. This is the last section in Unit 10, Learning Target 10C, which is all about solving square root equations. By the end of this lesson, you will be able to solve an equation with one square root, as well as solve an equation with a square root on both sides. So in this section, we're going to look at radical equations. So a radical equation is an equation that has a variable in the radicand. So remember, the radicand is the stuff that is underneath the square root. So our radicand would be whatever is underneath that square root. Some examples of radical equations could be the square root of x minus 5 equals 3. So in this case, the minus 5 is not underneath the square root, so just the x is our radicand. So that could be an example. Another example we could have is if we have maybe x minus 2 underneath the square root, then outside the square root we have plus 3 equals, let's say, 5. Both of those are examples of radical equations. To solve a radical equation, we want to make sure that we are first isolating the radical. And the reason we want to do this is we want to get the radical by itself, because in our second step, we are going to actually square both sides to get rid of the radical equation. So from there, what we want to do is, in isolating the radical, it means when I square both sides, my radical will end up going away. The third step would then be to solve for the variable. So I do want to clarify that isolating the radical, what that means is we're isolating the term with the radical sign. That does not mean I'm isolating just the x, but I'm trying to isolate the term with the radical. Let's look at some examples. So for all of these, it says solve the following. In our first example, we have the square root of x plus 7 equals 16. Our first step is to isolate the radical. In example 1 here, is the radical isolated? So in this example, the radical is not isolated because we have that plus 7 that is also on the left side of the equation. So our first step is to isolate the radical by subtracting 7 from both sides, and we get the square root of x equals 9. Now we have isolated the radical, since the only thing left over on the left-hand side is the radical term. Our next step from here is to actually square both sides. So I'm going to apply the square function to both the left and the right side. And I can do this because I'm doing it to both sides, so I'm still keeping the equation balanced. The reason we're applying the square is we know that the square and the square root cancel each other out. So on the left side, we just get left with x, since the square and the square root cancel. And on the right side, 9 squared is equal to 81. And in that same step, we actually isolated our variable for this first example. We can always check this answer by substituting it back in and making sure that we get a true statement. All right, let's look at example 2. So in example 2, it says the square root of x minus 5 equals negative 2. Is the radical isolated in this equation? So in this example, the radical is again not isolated since there is that extra minus 5. So to isolate this radical, we're going to add 5 to the other side, and we end up getting the square root of x equals 3. Our next step from here, now that we've isolated the radical, is we want to go ahead and square both sides. So as long as I do it to one side, I do it to the other, then I am keeping my equation balanced, and this is fair. On the left side, the square root of x squared would just leave us with x, since the square root and the square cancel, and then 3 squared would give us 9, and we've also solved for our variable at the same time. So in these first two examples, the radical was not isolated, but since x was the only thing underneath the radical, once we squared both sides, we actually solved for the variable. Let's look at example 3. So example 3 says the square root of x plus 7 equals 4. What do you guys think? Is the radical isolated already? So in this case, the radical is already isolated since we have the square root by itself on the left side. So the difference with example 3 compared to 1 and 2 is that the plus 7 is underneath the radical sign, which is why this term is isolated in example 3 versus in example 1, it was not isolated. So the first step I'm going to do then is actually square both sides. When we do this, again, the square and the square root cancel, so I end up with x plus 7. So the stuff underneath the radical, that radicand, is not going to change when I'm squaring it. It's just canceling the square and the square root. And then that's going to be equal to 16 from the 4 squared. Our last step here is to solve for the variable by subtracting 7. When I subtract 7, we end up getting x equals 9. Let's look at example 4. So example 4 says the square root of 2x plus 1 equals 5. Why don't you guys pause the video and solve example 4 on your own first? Okay, let's check example 4. So in this case, our radical is already isolated. It's the entire 2x plus 1 is underneath the radical sign, and that's the only term that's on the left-hand side. So right off the bat, we can go ahead and square both sides. That way, the radical sign will cancel with the square, and on the left side, we end up with 2x plus 1, and then on the right side, we get equals 25. From here, to isolate the variable, we want to subtract 1 and get 2x equals 24, and our final step will be to divide through by 2 and get x equals 12. So the one thing to keep in mind is when you're squaring, don't forget to square the left-hand side as well, because it would not be correct if we only squared one of these two sides. So just make sure as you go through each step that you are squaring both sides. Let's look at some more examples. So in example 5 here, it says the square root of x minus 3 plus 10 equals 12. What do you guys think? In example 5, is the radical already isolated? So in example 5, our radical is not isolated because of the plus 10 is also added to that side. So to isolate the square root, I'm going to subtract 10 over, and we get the square root of x minus 3 equals positive 2. Now that the square root is isolated, we can go ahead and square both sides, and we get the square root of x minus 3 squared equals 2 squared. The square and the square root cancel each other out, and we get left with x minus 3, and then on the right side, 2 squared will give us 4. From here, to get x by itself, we're going to go ahead and add 3 to both sides, and we'll end up with x equals 7 as our final answer. Let's look at example 6. So in example 6, we have the square root of x plus 4 minus 3 equals positive 2. Why don't you guys pause the video and solve example 6 on your own first? So in example 6, we need to have that square root isolated, and it is not yet. So I'm going to go ahead and add 3 to the other side to get that square root term isolated. So we get the square root of x plus 4 equals 5. Now from here, I can't move that 4 over yet until I get rid of the square root. So to get rid of the square root, that's why we square both sides. The square and the square root then cancel, and we're left with x plus 4 on the left side, and 5 squared gives us 25 on the right side. So we want to make sure that we can't move anything else over to get x by itself. If it's underneath the radical, we first have to get rid of that square root sign by squaring both sides before we move anything else over to the other side. Our last step here is to subtract 4, which we can do now since the square root is gone, and we end up getting x equals 21 as our answer to example 6. Okay, let's look at our last two examples. So these guys look a little bit different since I actually have two radicals. So in example 7, we have the square root of 5x minus 11 equals the square root of x plus 5. In this case, I actually have both radicals already isolated since I have a radical on the left equals the radical on the right. So right off the bat, we can go ahead and square both sides. What's going to happen then is that the square roots will completely cancel out. So the square root on the left side will cancel with that square, and we get 5x minus 11. And then the square root and the square on the right side will cancel, and we get x plus 5. So we wouldn't want to actually subtract over and get all the square roots to one side, because when we square that, then we'll actually produce even more square roots in the process. So this problem was nicely set up since I had a square root equaling a square root. So when we go to square both sides, then we do get rid of all the square roots. From here, we're going to isolate x, so I'm going to subtract our x from both sides to combine some like terms. So I'll get 4x minus 11 equals 5. Then add the 11 to the other side and get 4x equals 16. Then to get x by itself, we're going to divide through by 4 and get x equals 4. Let's look at our last example. Example 8 says the square root of 7x minus 4 equals the square root of 5x plus 10. Why don't you guys pause the video and solve example 8 on your own first. So we have one of these cases where we have square root equals square root. So let's square both sides right away so the square roots can cancel. And we end up with 7x minus 4 equals 5x plus 10. Now that we've gotten all the square roots to cancel, I can start combining like terms. So I'll subtract the 5x over and get 2x minus 4 equals 10. Adding the 4 over, we get 2x equals 14. And then our last step will be to divide through by 2, and we get x equals 7 as our final answer then in example 8. This is the end of Unit 10, where we did lots of problems about square roots and radicals and simplifying them, and then in this last section we learned how to solve radical equations.